So far you have been learning about electron domain geometry, molecular geometry and bond angle. This video will introduce you to hybridization and also will talk about pi and sigma bonds. So let's now understand hybridization. What is it? Consider CH4. The outer electronic configuration of the central element carbon is shown as in the diagram over there. It has two s electrons and two p electrons. So in general what happens is one of the electron from s is pushed over to the empty p orbital, and we always deal with the excited state of carbon, in which I have four unpaired electrons, one in the s and three electrons in the p orbitals, and that is the reason carbon can form four bonds. And the other element, hydrogen, the outer electronic configuration of hydrogen, it will have each one will have one s electron. So I will have four 1s electrons from hydrogen as shown over there. Now the bonding has to take place between carbon and hydrogen. So how will it happen? So one of the bond from the hydrogen will overlap with one of the electron in the carbon. So the same thing happens with the p electrons of carbon overlapping with the s electron of hydrogen. So verbally, if I write it down, overlap takes place between the 2s of carbon and 1s of hydrogen, and then 2p of carbon and 1s of hydrogen, 2p of carbon and 1s of hydrogen, and 2p of carbon and the last one s of hydrogen. So basically what has happened is one bond is formed by the overlap of s, and the three are formed by the overlap of p and s. So in general then the three bonds should be same and one of them should be different. But what we actually find is all the bonds in methane are same. How is this possible? Let's go ahead and learn how is that all the bonds in carbon are same. So we just saw that all the four bonds in methane are same. So how is it possible? Consider the electrons of carbon, 1s and 3p. What they happen is they all combine together. The 1s and the 3p orbitals, they mix together and they form four new orbitals, and we call them as hybrid orbitals. And since 1s combines with 3p, we call them as sp3 hybrid orbitals, which are identical. So now I don't know, there is nothing like an s or a p. They combine together and I get an sp3, and all the four sp3 orbitals are same. Now these four identical sp3 orbitals overlap with the s of hydrogen. So one of them overlap with one s, the other one overlap with another s, and so on, and I get four sp3 hybrid orbital overlapping with the s of hydrogen bonds, and hence the four carbon hydrogen bond in methane will be same. So sp3 hybrid molecule has a tetrahedral electron domain geometry. Because four bonds, the electron domain geometry is tetrahedral. So basically what happens is the orbitals mix together and one hybrid orbital is formed, and hence all the four bonds formed are identical. So the table over there refers to the same table which you have been seen in the previous videos. The only thing which is added over here is the hybridization also. So depending on the electron domain geometry, the hybridization for AB2 is sp, for AB3 it is sp2, for AB4 it is sp3, AB5 it is dsp3, and AB6 it is d2sp3. And you need to remember these hybridization also. This is basically the consolidated list in which all the bond angles are there. You have the electron domain geometry, you have the molecular geometry and the hybridization, and one example of each is also given. So keep it in front of you whenever you are doing molecular geometry question. It will be pretty helpful. So let's continue with it and learn what is hybridization and pi bond. So far you are familiar with only one kind of a bond, which is a single bond. So start with, consider the molecule C2H4, and we know that the outer electronic configuration of excited carbon is shown over there. Now what happens is, in this case, the 1s and the 2p orbitals, they mix together and form 3 new hybrid orbitals, and we call them as sp2 hybrid orbital for each carbon. There are 2 carbons here, each one gets this. And you notice that I have left out one p orbital, only one s and the 2 p's combined, and that results in 3 sp2 hybrid orbitals. So you should be, this is different from the previous case where we get we had sp3. So these 3 sp2 hybrid orbitals, they overlap as shown below. One of the sp2 of carbon 1 overlaps with the sp2 of carbon 2, and then I am left with 2 sp2 orbitals on each of the carbon, which overlap with the hydrogen as written over there. So now I am done with the 3 sp2 hybrid orbitals of each carbon. Now what is left? I have not used up the p electron which is over there. So that p electron has to be used. So the p electron which is over there, the left, the p electron which is left is shown as in the figure. It has a dumbbell shape, and then these overlap sideways and a pi bond is formed. So basically a pi bond is formed with the overlap of two p orbitals sideways. The hybrid orbitals are not involved in this. So we will continue further and identify these, what are the different kinds of bonds we have over there. Let's continue with the hybridization and pi bond, continuing with the same molecule CTH4, which is shown over there. So in this molecule, we know that the carbon is sp2 hybrid. We just did that, and it is sp2 hybrid. Even the other carbon is sp2 hybrid. So let's identify the bonds formed over there. The bond which is below over there, it is formed by the overlap of the hybrid orbitals sp2 and sp2, and we call it as a sigma bond. The other bond, the carbon hydrogen bond, is formed by the overlap of the sp2 and an s orbital, and that's also a sigma bond. So what happened to the double bond which is over there on the top? It's formed by the overlap of the 2 p orbitals, and we call it as a pi bond. So it's very important that in any molecule, the bond which is below, if you have a double bond, the bond which is below is a sigma bond, and it is formed by the overlap of hybrid orbitals, and the bond which is above it is a pi bond, and then that's formed by the overlap of the p orbitals. And pi bond can never be formed by the overlap of a hybrid orbital. This is a thing which you should remember. Let's go further. Let's go to the next compound, C2H2. Okay, so the structure is as shown. So let's identify the hybridization of the carbons. That carbon over there, the hybridization is sp. Looking at the number of bonds, I have one here and one there, therefore it's sp. The other carbon is also sp. Or if you have a triple bond, that carbon will have an sp hybrid orbital. So the bottom one is formed by the sp-sp sigma bond, and the carbon hydrogen bond is formed by the overlap of the sp-s sigma bond. So what about the two double bonds, two bonds over there above the sigma bond? Both the bonds are pi bonds. So it is important to know that even in a triple bond, one can be a sigma bond, the other two will be a pi bond. So if you have a, how do I remember all these things? A carbon-carbon single bond will be sp3 hybrid, and it will have a tetrahedral geometry around it. A carbon-carbon double bond will be sp2 hybrid, and it will have a trigonal planar geometry. And a carbon-carbon triple bond will have a sp hybridization with a linear geometry. So these are some, the table is something which you have to remember. So now we will go further and do some examples on identifying the hybridization of the molecule. Let's do some examples. Take an example and predict its geometry, hybridization of the central atom and the bond angle. CHI3 is the example. The Lewis structure of CHI3 is as shown over there. It has one central atom and 4 atoms surrounding it, and hence it is a AB4 type of molecule. So I don't see any, the electron domain is tetrahedral, and since I don't see any lone pair, the molecular geometry for 4 atoms, and hence it is tetrahedral. And the hybridization for a tetrahedral geometry is sp3, and the bond angle is 109.5 degrees. This molecule will be polar because the presence of 1 hydrogen and 3 I, the bond polarity will not cancel, and resulting in a polar molecule. Or I can say that the surrounding atom is not same, hence the molecule will be polar. Let's do some more examples. I'll put it in the table form. For example, HCN, the Lewis structure is given over there. The electron domain geometry is linear, and the molecular geometry is also linear because the central atom carbon has no lone pair on it, and a carbon with a triple bond will be sp sp hybrid. The next example, ClF3. The Lewis structure has 3 bonds and 2 lone pairs, so the electron domain geometry is trigonal bipyramidal, and the shape is T shape, and the hybridization of the central atom for a T shape will be, for a trigonal bipyramidal, is dsp3. You need to memorize all these. XCF2, it's trigonal bipyramidal based on the Lewis structure, and it's linear, and the hybridization is again dsp3. One more example, BRF5, and with 1 lone pair and 5 bonds, it has an octahedral structure, and hence the hybridization is D2sp3, and the molecular geometry is square pyramidal. So in this molecule is given to you, you need to identify how many pi and sigma bonds are there. The first one is CH3CH double bond CH2. Double bond, one of the bond in a double bond is a pi bond, the other one is a sigma bond. Therefore, I have 1 pi bond. So count the rest of the bond. I have, if you want, you can write it as an expanded structure and check it out. I have 3 hydrogens attached to the first carbon, therefore 3. And there is 1 bond between the 2 carbons, 4. Then 1 hydrogen attached to the central carbon, 5. And then in the pi bond, there is the lower bond is a sigma bond, 6. And then 2 hydrogens attached to the carbon on the right hand side. Therefore, there are total 8 bonds. So this is the way you need to count for all the other molecules also. So the next one, it has 9 sigma bonds and 2 pi bonds. And acetic acid, CH3COOH, it has 1 pi bond. The 1 pi bond is between the carbon and the oxygen. The COOH group is generally written as C double bond OOH. So the double bond exists between the C and the oxygen. And ethyl alcohol C2H5OH has no pi bonds. HCl, there will be a triple bond between carbon and nitrogen, and hence it will have 2 pi bonds. Carbon dioxide has a double bond between the carbon and the oxygen, and hence it has 2 pi bonds. CH3CH2Cl has no pi bonds. And the last compound, because of the presence of 2 double bonds over there, it has 2 pi bonds. Identify the hybridization of the carbon in the following molecules. So the first molecule given over there, we need to identify the hybridization of each one of them. The first one is sp3 because it has only single bond around it. The second one has 1 double bond in it, therefore it is sp2. The third one has got 2 double bonds. 2 double bond is actually 1 triple bond, and hence it is sp. And the next carbon is sp2 hybrid because it has 1 double bond on it, and the last carbon is sp3 because of a single bond. So the next molecule, similarly, look into the number of bonds around the carbon. A single bonded carbon is always sp3 hybrid. The oxygen over there is also an sp3 hybrid molecule, and the 2 carbons of the second molecule will be having a tetrahedral geometry, whereas the oxygen, in spite of it being an sp3 hybrid orbital, it will have 2 lone pairs on it, hence it will have a bent molecular geometry.